Okay, so let me remind you where we left off and also just remind you of some definitions. So important definition number one was our definition of the projection operator. So the projection operator acting on a dynamical variable B. B could be time dependent or time independent is okay, so and these are all at time 0. Okay, this is at time 0. So if I don't write a time argument, it's time 0. Okay, and also the fluctuating force can be written as right, that's a little bit nicer than the way we were writing it. But remember, Q is 1 minus P. So it's the complementary projection operator. And so remember, what the way we had written this is e to the 1 minus P LT times I 1 minus P LA. But I LA is A dot. Okay, so this really should make it clear what the fluctuating force is. A dot is like a force. Q projects it into the space orthogonal to the main projector, and this propagator propagates it in that space. Okay, so if P projects out the slow character, like the hydrodynamic character of a mode, then the fluctuating force is the force propagated in the orthogonal space that's orthogonal to that slow character. Okay, and where we had gotten at the end of the last lecture were a generalized Langevin equation for the variable A, which is exact. This is and we're going to actually make A a vector, and omega is a matrix. So I'll just write it like this, because A is, in the lecture today, A will be a 2-component vector. And then there was a memory term, or a generalized friction term, a memory function, and a fluctuating force, right, which is this. Okay, so that is exact. And if we multiply by A at time 0, let's say on this side, and we multiply everything here by A at time 0, and we take the thermal average, then this is the time derivative of the correlation matrix and this is exact. Remember that at any time, the overlap of A and F of t is 0. Because the projector projects onto the space of A, and F at all orders is a function of the complementary propagator, the complementary projector 1 minus P. So always the 1 minus P acting on A is going to give us 0 at any time. Right? So when we multiply by A, here the inner product of A and the fluctuating force is 0, and this term goes away. And so this is our starting point equation for our analysis. And the definition of the memory function, which is very important. So K Okay, it's the inner product of the fluctuating force at 2 different times, normalized by the the A matrix if, well, these will be vectors and these will be vectors. So this will, in our case, this will be a 2 by 2 matrix. This is a 2 by 2 matrix. We'll calculate what these things are. And lastly, let's see, the I omega matrix is really just this. Okay. Also, before we go on, this is a complicated object, not just because the fluctuating force is complicated, but also the propagation here is with respect to the anomalous or complementary propagator, right? So this explicitly, this is these are vectors, and this is a 2 by 2 thing times. This is just a static normalization. So this is propagated with this Q. And I had mentioned the relationship between equations of this form and something like the Schwinger-Dyson form. And one of the things in order to prove the equivalence is showing that you get something like the self-energy, but dealing with the fact that you have to sort of remove the Q. And you can do this systematically, but it just takes work. So yes, there's a relationship, but no, it's not a short amount of work. So yes?
Your A is now a vector?
In our original derivation, A was just some dynamical object.
Okay, then if I choose a normal vector to A, then that means A overlap A is not invertible because it has an eigenvalue normal. So what do you mean the inverse now in terms of the vector?
So the normalizations that we have are always going to be this. And the way I want you to think about this is that if A is, let's say in our case, A will be a 2-component object. So it's going to be, let's say, A1, A2. Then this matrix is, the AA matrix is just, A1 squared, A1, A2, A2, A1, A2 squared. I mean, in just a shorthand notation. And so this may or may not be invertible. And we'll see that it is invertible for the A that we choose. Okay, so actually, what is the A that we chose right at the end of class? I said that we should take our A to be the fluctuation of the density and the longitudinal current. Okay, and to remind you, the fluctuation of the density is defined as right, this is just the average of rho k. So that's the density fluctuation, and the longitudinal current for wave vector k is okay, so I'm going to take this. Obviously, this is proportional to the derivative of this. The proportionality constant is I times the magnitude of the vector k. Right? So, and that's just the continuity equation. JL dot is equal, or I times k is equal to rho k dot. Okay, so are we good? We're good. So now what we have to do is start calculating things with this A. So the first thing that's easiest to calculate is actually what is this matrix. Right? We need this matrix, then we'll calculate this guy, and then we have to deal with what, and then we should ask explicitly in terms of this A, what is the fluctuating force? Okay, and what is the fluctuating force matrix? And then from that we're almost ready to do mode coupling. Okay. So also in our, this is important, let's explicitly write out what the correlation matrix is in this basis. So the 1, 1 component is just proportional to the intermediate scattering function. And then the remaining components are related to the time derivatives of the intermediate scattering function. It should be minus, minus. Okay, so that's our C of t matrix, and there's a missing bracket here. Okay, so this is f, and this is like proportional to the time derivative of f, this first time derivative of f, this first time derivative of f, the second time derivative of f. So it's easy to ask, what is this at time 0? That's actually going to be the AA normalization that we have to use. So can you immediately see or not that these, at time 0, this guy and this guy have to be 0 by symmetry? Okay, so what I mean by that is since J is proportional to the time derivative of rho, what we actually have is something that's, for those elements, for the off-diagonal elements, is just proportional to this, where this is some dynamical variable. And when you have a static time correlation function, these are both at time 0, and this is time derivative, right? You can always integrate by parts and move the time derivative here with a minus sign. Okay, so this is equal to the, but yet these are classical variables at the same time, so I can just move them like this. Okay, so the static correlation, meaning at time 0, for this guy and this guy, is 0. Right? So the normalization matrix, or the AA matrix, is at least diagonal. Now, the question that was asked is whether it's invertible. It will not be invertible if one of those elements is 0. Right? But actually, you know what this element is at time 0. It's n times s of k, right? So this at time 0, right, at time 0, this is 0, this is 0, this is n times s of k. This we can just work out from our definition there. Okay, so it's basically going to be the correlation of sum over I k dot ri dot. And by the way, I think this should have a 1 over m in its definition. Let me see. Right. So it should have a 1 over m, but this should be a p. So it actually is correctly defined as I wrote it, but I'm just going to write it like this. Okay, it's the same thing. P over m is v, so or r dot. So this is the same. So it's going to be this. Right, and this. Right, so at the equal times, the same time at time 0. And you can easily work this out, that if this is the velocity on particle I, this is the velocity on particle j, the correlation function of vi, vj, let's say x, because k is picking out one direction. So this is just like along one component. This is delta ij times kt over m, classically. So this is equal to, very, very simply, n kt over m. The kt over m comes from the velocity, the static correlation of ri with rj, and the factor of m comes from the additional sum over all I that's left over. You know, when you even when you have the Kronecker delta, you still have a sum over I and j. So one of them gets rid of the delta, but the other one sums over all particles, and you get a factor of n. So this matrix is invertible. At time 0, it's n s of k, 0, 0, n kt over m. And so the inverse of that is just 1 over this, 1 over that. That's a inverse. So this would be m over n kt. Okay? Any questions?
Is there a minus sign in
No, there shouldn't be a minus sign. The minus.
negative k to the second one? Plugging in minus k to the...
This is minus k here, but this is just the k. This is just the k hat vector, picking it along a positive k. Right? The complex conjugate only affects the phase. Okay. So what else do we need? Now let's calculate the I omega matrix, which is the matrix of A and A dot times the normalization, which we now know is 1 over n s of k 0, 0, m over n kt. Right, so we have to calculate what this matrix is. So this guy is delta rho minus k, delta rho dot k, delta rho minus k, dj k longitudinal dt, j minus k longitudinal times delta rho k dot, and all at the same time, right? All at time 0. All right, it's going to be whatever this 2 by 2 matrix is times this diagonal matrix. Let's see, it would be the, actually there should be, right, this should be, I think this should be this. Right. Right, because we have A and A dot. Okay, so let's calculate what this matrix is. You can use you basically, for all of these calculations, you just use things like this. Okay, you either know what the thing is, or you move dots around and just take averages that either correlate velocities and give you factors of kt over m and so on. So I'm just going to skip ahead and write this out. So obviously, looking at this matrix, this is now 0, and this is now 0 by time symmetry, and these elements are non-zero. These are like j, j, and jj, right? I can move this ddt over here, and this is like a jj correlation.
Put the board up, the board.
Yes. Good idea. So if you use the same kinds of simple algebra, what you get is this. This is the norm of the k vector that comes from taking the time derivative of the density, right? It brings down a k. So this is equal to that's what that matrix is. Okay. So now we want to calculate what the fluctuating force is. So first let's look at what the fluctuating force at time 0 is. Remember the definition of the fluctuating force at time t is e to the I q L t q a dot. Okay? At time 0, we can just set this to 1, and we just have q a dot, which is actually just a dot minus I omega times a, right? Because it's 1 minus p a dot, right? So the 1 gives us the a dot. P acting on a dot gives us a dot normalized by a, which is just I omega. So what is this? This is this is a dot minus this matrix 0 I k kbt over m s of k 0 times times del rho k j longitudinal k, right? And we can do this matrix times vector. And so what we find is that the fluctuating force is equal to a vector whose first component is 0. Why is that? The first component of this just gives us the continuity equation back. This is one of the reasons why we defined A this way, in terms of something which is a density fluctuation, and the next element is the time derivative of the density fluctuation. So if you look at the first element of this, what is it? It's 0 times ik times jl. So del rho k dot minus ik jl is 0. So the first component of this vector is 0, and the second component is something funky looking that you wouldn't sort of guess to write down. But I'll use the notation R, and you can just do the very, very simple matrix algebra. R is equal to the time derivative of the longitudinal current minus I k kt over m times s of k times the density fluctuation. This is important. Okay? So now we have, much of what we need to proceed. So remember we had an equation like this. Right? That's our equation. Now we know almost everything inside this equation. We know what C is, we know what I omega is, and we can calculate the memory matrix. And because it's basically just the autocorrelation function of this vector with itself propagated with e to the iqlt, k as a matrix is just 0, 0, 0, and then m n kt times r of minus k e to the I q l t r of k. Right? Where does that come from? I just make the r vector autocorrelation function propagated with the q, and I get 3 0 elements because of this 0. And the fourth element is just this r propagated with this stupid propagator. Okay? It comes from the normalization. Remember that this is fluctuating force normalized by AA. So it's exactly the normalization term of that element that came from right here. That's actually important because actually usually when I'm deriving things, I always forget that. And then you'll get really incorrect answers. So the normalization matters. I mean, n is important, for example. OK, so what we're going to do is we're going to just look at the 2/1 matrix element of this to get a scalar equation. Yes?
So sure that K here is Boltzmann's constant?
K is Boltzmann's constant. Yeah, you know what? So I have two options. I can switch to Q for wave vector, but it's too late for that. So I'll just put a B everywhere.
Stick like an arrow above every K wave vector.
Yeah, but there are actually K scalars too. Like this is only a function of the magnitude of K, and this is I've been writing it as magnitude for that reason. But so why don't we just put B for every time there's a Boltzmann's, B is good. I could use beta. But then I always get dyslexic about beta and 1 over beta. So as long as you correct me, I can do that. But I think this works, right? I mean, we sort of know what K sub B is. Yes?
Can you give us a big picture, short answer of what is going on here?
Yeah. I think, well, we're almost where I think I can give you a bigger picture. And where the bigger picture is going to come from is what does this mean? I mean, why is this the component of the fluctuating force? And this, I sort of alluded to this at the end of the lecture yesterday, that hidden in here are pairs of density modes. And but let's first write down what the scalar equation is if I take the 2/1 element of this, right? And then I have, this is Einstein summation notation, alpha 1, right? I'm just summing over all alpha, and then 2 alpha, alpha 1. And then there'll just be one term that's left, and it's actually gets us very close to a very useful equation for the intermediate scattering function, which is this. So this is not Boltzmann's constant. Right, that's the wave vector. Tau. Okay, so I moved the memory term over to the left-hand side, so this is a plus, and everything is 0 on the right-hand side. And this is the 2/1 element of this after we've put in all the terms. Right? The 2/1 element is the one where this is actually doing something. Okay? So this equation is a generalized Langevin equation for the intermediate scattering function. If we knew what this correlation function was, we would be done. We would have the exact description of the intermediate scattering function. For example, you can actually simulate this on the computer. And there are nice algorithms to simulate what molecular dynamics does. I'm sure Ludovic didn't talk about this when you've got the anomalous propagator. There's actually some very smart ways to do that. And then you can go ahead and plug this in and calculate it, and I assure you, you will get back what you get from your MD simulation. So maybe that's actually a faster way this should decay. But as we'll see, there are slowly decaying tails in this that means that you don't get a free lunch. And those are all where all the interesting effects are. A few things before we answer the question, what is this and what does this all mean? Even if we didn't know what it meant, this starts to look useful. It almost looks like a closed equation for a quantity that we care about that has interesting signatures of glassy behavior embedded in its dynamics. There's another thing, which is even if we dropped this term, already there's something interesting here which shows that this is, so how many people have heard of Feynman's theory of superfluid helium? So in superfluid helium you can measure, you can do the same kind of scattering experiments, right? You can do neutron scattering, and you can measure density fluctuations at very low temperatures. Let's say below the lambda transition at 3 Kelvin or something like that, at 1 atmosphere pressure. And you can measure in the Fourier transform of the density-density correlation function. So you could take the intermediate scattering function and Fourier transform in time, and then you get the dynamic structure factor, right? You get S of k and omega instead of fkt. And you can measure the wave vector dependence of the highest peak in that dynamic structure factor, right? And it looks something like this. So we'll call that okay. So as a function of k, in this, as you go below the superfluid transition, if you Fourier transform this to get S of k and omega, and you can measure this, and then you, at each wave vector, you look at the peak of this thing, and you calculate for each wave vector where the peak occurs. You can map out what's called the dispersion for that, which is like the energy associated with the quasi-particle. Yes? This one? Ah, good. The problem is when I teach, we never have 3 sliding boards at once. I'm just not skilled at. Okay, so what's interesting about this curve, so down here we expect this energy as a function of k to be linear in k, and these are just phonons in the system, so they're just sound waves. But then there's a peak at a finite k in this dispersion and a minimum, and this is called the Rotan minimum. Okay? And Feynman's theory is so very simple, it's already embedded in this, essentially, which is that he says that the excited state wave function is just the density fluctuation times the ground state wave function. Doesn't know what the ground state wave function is. But then from using very, very simple quantum mechanics, just a commutator, you can get what the dispersion is. And the dispersion works out to be basically k squared over m s of k. Right? And there's an h bar squared here instead of kBt. But it works out for the same reason, meaning that if I redid this Maury-Zwanzig approach for a quantum liquid, okay, and used that generalization of the projection operator for quantum problems, the weird one that I wrote out that you probably didn't internalize yesterday, this would come for free. So, and by the way, the reason why you have a Rotan minimum here is because S of k has a big maximum at this k, right? So you divide by a very big number, and something that's going up like k squared gets divided by something that's actually growing even faster, and you get this turn down. Okay, this is not an accurate theory for the dispersion in helium. The true dispersion looks, something like this. And actually, this theory would go on forever here, and it wouldn't turn over. But it's still a reasonable starting point. And so the mode coupling theory that we're going to develop for glasses actually was first written down to apply to superfluid helium at 0 temperature. And so it already has, there's already physics in this I omega term that's interesting. So the actual origin of the name Rotan is much more subtle. So the picture that Feynman had, which comes nowhere in what I told you, because actually if you think about this, that doesn't seem to be anything related to interesting quantum mechanics. It's just the property of a cold fluid. A cold fluid has a high peak in S of k, and you'll get a Rotan minimum. And so what does that have to do with quantum mechanics? It's very unclear in reading Feynman's paper, which doesn't really go into this. He does have a picture for what this wave function means in terms of quantized vortices in the liquid, which I think later Nozieres and Pines proved to be wrong. And so it's not so clear what the physics means, but that's one reason why this is called a roton, because there's a picture of quantized rotational motion that comes from this. There's actually, it's very strange, there's still about 6 people in the world that are arguing whether or not the dip that you see in the dispersion is really related to superfluidity or not. Yes?
So, I mean, when we get second sound, is there a footnote on the right? Does that come out of, like,
Nothing about second sound comes out of a theory like this. Yeah, this theory is incredible. It's so simple that our theory already has more in it because it already has this just as the harmonic oscillator term. One of the features, though, that this theory that we'll outline now has that no other theory of the dispersion, and by the way, the dispersion in superfluid helium is not that interesting because it's very hard to be sure that you can connect it to the superfluid fraction in the medium. You know, you're always dealing at finite wave vector, and it's not clear that that is really probing the interesting quantum nature of the superfluid part of the liquid. But one thing that this theory gets right, or the mode coupling theory that we'll get to in like 10 minutes or more, gets right that theories like Feynman's doesn't have is this bending over of the spectrum, which is called Pitaevsky bending of the spectrum, and this comes from the memory function term. Okay, so let's now ask what, so the equation there, and we just have to deal with the memory function. So let's actually ask what the fluctuating force looks like. So this is and this, we can just calculate what that is. That's the time derivative of the longitudinal current, and there are 2 terms in that. So So one term actually looks like a force, like a real, like, you know, Newton's equation force. dp dt is the force. Okay, so this is the force on particle I. And this term looks like a kinetic energy. So it actually looks like the fluctuating force has 2 terms in it. One of them is a force-like term, and one of them is a kinetic energy-like term. Okay, and the kinetic energy-like term should fluctuate very rapidly. But the force term can slowly evolve. Okay, and in particular, this is something that I had said yesterday. If we think about what this is in our problem, we want to write it in a suggestive way. This is just the regular force on the particles. If I take the gradient acting on the interparticle potential, right, I can write it in Fourier space like the Fourier transform of the interparticle potential, I times the k wave vector, and then a pair of density modes that are propagating in opposite directions. Right? This, you should be able to show this just from algebra. How if I Fourier transform this, I'm going to get an e to the I k dot Ri and an e to the minus I k dot Rj, right, in my switching from I and j in real space to k, right? And then when I take the derivative, that's going to bring down a k. Everything else is going to be left in terms of the Fourier transform. So this is just the standard thing. So, but basically what it means is that the fluctuating, if we ignore this, if we assume this decays very quickly, the dominant term at long times in the fluctuating force are co-moving density modes, a product of density modes that are propagating in opposite spatial directions. So basically, coming back to the meaning of this equation, basically this equation more or less looks like a harmonic oscillator equation, a damped harmonic oscillator equation for FKT with a memory term, and the memory term is the dominant component of the memory term are 4-point density correlations, right? Because it's like a force, and a force is a pair of densities. Okay? So this is where the mode coupling aspect comes in. What we're going to do now, if you remember, the propagator there is the anomalous propagator. The anomalous propagator is the one that's propagated with this Q. And we're going to make an approximation that we are going to project again with a new projection operator this term onto pairs of density modes. And then we're going to drop the anomalous propagator because we've already projected out single densities and pairs of densities. Okay, so we've already removed those components. So we don't have to worry about the component on single densities anymore. And we can replace the e to the I QLT with e to the ILT. So basically, the approximation is going to be that e to the I QLT is approximated as P2, and I'll define this projection operator in a second, e to the ILT P2, but in words, P2 is going to project onto pairs of densities, because that's the dominant component of the fluctuating force. And the reason I can get away, which actually I'm just saying this in words, I can't get away unless I prove I can get away with it, but I will drop the Q here, is, as I said, we've already used the regular projection operator to get rid of del rho, and now we're going to project onto the space of rho rho. So in this space of single densities and pairs of densities, I don't need to remove single densities anymore, which is what the Q is doing. Right? It was 1 minus P. So I can just drop the P part. And that's going to get rid of this problem of the fact that the time dependence is weird. Okay, and I just have to compute what is well, first I have to define this P2, and then compute what is P2 acting on the fluctuating force, plug that all in, and I'm done. I just have to compute a lot of terms, static terms like these kinds of things, and we'll have a closed equation for the density correlators if I make one further approximation, which is a mean field approximation. That's the most important thing, which is now this is going to be a 4-point correlation function. It's going to be something like density, 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 density. Okay, because I'm going to project onto pairs of densities on either side. That's going to project the fluctuating force here and the fluctuating force here. Then I'm going to propagate the two densities on the right. That is not a closed equation, but if I make some sort of Gaussian approximation where I approximate this as products of rho and rho t, then those are each proportional to fkt, and I get a closed nonlinear equation where the memory function is proportional to the square of the intermediate scattering function itself. Okay, so let's do that quickly because it's boring and it's in my notes, and we're so far behind that I'm worried. Okay, so as we said, in this fluctuating force, in this memory function, excuse me, we're going to approximate this as projected fluctuating force, e to the ILT projected fluctuating force. And this second projector, P2, acting on any variable, and this is messy looking, it's going to be a sum over K1 through K4, just to be very general. That's what it's going to be. It looks intimidating because there's lots of wave vectors, but I'm just projecting onto pairs of density modes and normalizing it by that. But the normalization is now a 4-point density correlation function. And obviously, K1 plus K2 plus K3 plus K4 has to add up to 0 to conserve momentum. And all of the algebra for this, what this projection works out to be, is written down both in the published notes that I wrote with Patrick Charbonneau, but also in the handwritten notes to a lesser degree that I think are on the website, but I didn't check. So basically, when you project this projector onto the fluctuating force term, you get something that looks like this. And I'll define Q in a second. Right. You can relabel one of the K's as a Q term, and then everything else is related to just these overlaps. Right, I'm going to call this KQ now, just to, so I'm not confusing it with the K1 through K4 that I have. Okay, and what does this V work out? This is called the vertex. It actually is just the term that comes from, excuse me, this is not here. This is what the projection looks like, and this is the vertex. This I call VQ, K1, K2, and I'll write down what this is in a second. Okay, sorry about that. So basically, in the end, I get a double sum over two Ks, and I have plugged the fluctuating force in here. This should be Q now, right, in this notation. So this is a Q-dependent thing. It depends on the wave vector of the actual fluctuating force. And then these two density modes normalized by the 4-point density, which is this. So my B just here is RQ. And this is a static constant, okay, in the problem, and I have to work out what it is. I'm not going to work out for you what it is because it will take 40 minutes. But it's not any rocket science. It's just simple averages like the ones we already did to get the I omega matrix and the C matrix, and it's in the published notes that are online. You just tediously have to work out things like what is the static average of rho, or J rho, or something like that. And you get KTs and so on, S of Ks. Yes?
So you just replace B by...
Yeah, I'm just defining the projection operator on any variable to be this. Yes, you're right. There's a delta rho, delta rho. So this actually should be K1. This should be K2. Sorry, this should be 3 and 4. But this is still the vertex. Right? So basically what you get is you get a pair of density modes and then a bunch of static garbage. This static garbage divided by this actually together is what I'll call the vertex. Since we're not going to derive it, I'll write it down. It turns out actually with certain simple approximations, which are outlined in the lecture notes, and I don't have time to go into, this turns out to be very simple and is expressible just in terms of the static structure factor. So if I say that K is equal to K1 minus K2, then V Q K1 K2 is V, I'll write it in this notation, right? We can, if I use this, then I can write it just as a function of K and Q minus K, and then the vertex, which is just a static thing, is I times the density times Boltzmann's constant times temperature over twice the mass and the number of particles, and then Q hat dot K times what I'll call the direct correlation function, C of K. C of K is just 1 over the density times 1 minus 1 over the structure factor. That's a static correlation that comes up a lot in liquid state structure. And then another term, Q hat, okay, this is the vertex. Okay, so basically what we have now, if we make this approximation where this is the exact memory function, and I approximate this e to the IQLT as P2 e to the LT P2, I get something for the memory function which should look like the following. It should look like a sum over a bunch of wave vectors times the vertex squared, because I get one vertex for each projection, right? I'm going to get, and I think, no, I'll write it out here. Remember, I've got a correlation that's like R and then P2. So I can act this P2 on this R. Then I'm going to put an e to the I LT here, P2 acting on R. Right? For each P2 acting on R, I get a vertex. So I'm going to get like the absolute value of the vertex squared. Right? So it's like the Fermi golden rule or something. I get a coupling constant squared. And then, as Camille asked, and it's correct, there are pairs of densities left over, 2 density modes on this side, 2 density modes on that side, and the propagator is going to make 2 of them time dependent. And so the overall memory function is going to have the form of a sum over the vertex squared times a correlator that looks like this. And this is now regular time propagation. Mm-hmm. Right, so remember, this is always a problem with this when you've got it. Remember that the fluctuating force is K dependent. But then I define my projection operator in terms of K1, K2, K3, K4, the P2 projector. So I don't want to use K anymore for the wave vector associated with the fluctuating force itself. So I'm just going to call it Q for now. Okay? And so the Q that goes in here is the wave vector of the flux. So you can call it K. Right, and then the other ones would be K with labeled indices.
No, but why the hat?
The hat is just the direction. Why does it come out that way?
Okay,
It's just the unit vector along the direction of the vector associated with the fluctuating force. Right, and this one is not a hat. Right, so when I square the vertex, I'm going to get a K squared, and here I'll get a Q minus K squared. All right, so as any lecture that goes into the details of mode coupling theories always gets, this degenerates. but we're so almost done that the one last thing that I'm going to tell you is what I'm going to have to do. Here I've got a bunch of wave vectors too. Just schematically call them K1, K2, K3, K4. What I'm going to do is I'm going to make a factorization approximation. I'm going to assume that this is approximately delta K1 or minus K1 K3 plus delta minus K2 K4 times the associated F K1T F K2T. All right, I'm just going to make a pairing approximation. Since they were fluctuations, actually, those two are the only surviving pairings that you can make. Okay, so I'm not going to write it all down, but that's the spirit of it. This is the vertex. So I'm going to get something that looks like this, and then the remaining heart of the memory function is pairs of density of intermediate scattering functions. All right? So it seems bad, but actually it's really simple algebra. And as I said, all the algebra is in the JSTAT notes that are posted. So you can go through it if you want. But most of you will probably feel satisfied that you sort of get the idea where it comes from. And I'll write down the final equation. Remember, we were very close anyway. So we just needed an approximation for this term. And now we have it. It's going to be what I'll write down now. Okay. So here we go. Here's the final equation, which shouldn't be such a stretch of the imagination, given that most of this we wrote down. And some of it we actually even coherently derived, some of it less coherently. Let's call this Q now, right? We changed it to Q. Right? That's just this equation. And by the way, you know you can always switch. This is a function of tau, and this is a function of t minus tau. And you can make this a function of t minus tau, and this a function of tau just by changing variables. Like tau prime equals t minus tau. So this is the same equation that's over there. And now k in our mode coupling approximation works out to be okay. So I want to make some comments. So the V there is just this V. Okay. This is the intermediate scattering function at the wave vector Q minus K, and this is the one at wave vector K. And you sum over all K. So the final answer is a function of Q. All right, so this looks horrible, but actually it's really nice for a bunch of reasons. So the first reason is it is a fully first principles microscopic liquid state theory for which if you tell me what the temperature is, the density is, and the static structure factor, all I need then to do is plug that in, solve that equation, and get the dynamics out without anything else. Okay? And I'll show you pictures of what that looks like in a second. I don't also know if Giulio or Leticia talked about the exact equation for the dynamics of that is generated in the p-spin model. Did they? Okay, so I'll write down something that looks like that in a second, and then we'll talk about that. But actually, this is a nonlinear integral differential equation, right? It's like derivative of a function or second derivative times a term proportional to the function, and then under the term here is like the function squared times the time derivative of the function equals 0. So it's a very funny looking equation. But actually, I'll show you in a second, in a schematic sense, this equation is exactly the same as the exact equation that you get in fully connected p greater than 2 mean field spin glass models. And yet, I mean, this was known first. So in some sense, one of the motivations for studying mean field spin glass models was the people that really pushed the study of those models in the 80s, which in my mind started with Ted Kirkpatrick. He was someone who knew liquid state theory very much. And he wanted to make a model or study a model for which the dynamics of that model is exactly, here we've made some gross approximations, right? We did this second projection. We factorized things. There, as I'll discuss in a second, the dynamics are exact, okay? And yet it looks exactly like this. And then what you can do, which has been a huge cottage industry in the glass transition field, is to say, okay, we have a disordered spin glass model. Its dynamics in the high temperature regime are exactly like this. What are the other properties of the model? And that's led us to understand much more about entropy crises and things like that. And I'll very briefly talk about that. So I don't know if people have printed the notes out, but in the notes I've shown you some examples of how well this theory does when you compare it to actual computer simulations. So let me first just say what the properties of the model are. I actually outlined some of them at the very beginning of the lecture yesterday. Yes?
So, I mean, everyone told us that S of Q changed very little.
Yes.
From
Yeah. So how does this, right, I haven't yet told you what the equations give you, but your question is a good one. It might lead you to suspect that this equation can't describe anything like a glass. Right, so why does that happen? So there are two things. One of them is that the density and the temperature do appear here, and they're changing. Okay, but they look like they might even be changing in the wrong way, right? Well, at least for temperature. If I fix the density, like I want to do a mode coupling calculation for a Leonard-Jones simulation, and I want to do it at 1.2 density for the Cobb-Anderson model. I put this in here. It looks like this term is actually, it's getting smaller. So it's making the memory function smaller. Okay, but in here you've got this, structure factor, and as you said, it's changing very little, right? So the peak is getting a little sharper. The secondary peaks are getting a little bit sharper, but nothing else seems to be changing. So how do you get anything out of this equation? And the real answer is it's nonlinear. Okay, so a very, very small change in the static structure factor can lead to a huge change in the feedback. Okay, and that's the essence of the equation. So let me first talk about this in a schematic sense. So let's say I say that the structure factor is approximately dominated by, the first peak, and I just make it equal to a delta function for the first peak. If I do that and I plug it into the vertex, I can write down an equation where I'm just thinking about a single structure factor. So I'll just call that phi. And the equation that I have right there is of this form. Right? That's what the form of this equation is. And you can actually derive what that constant lambda would be from, how you schematically alter the peak of the structure factor and this constant A. Okay? This equation is almost identical to the exact equation for the dynamics in the high temperature phase of the p equals 3 spin glass model. The only difference is that this is a second derivative and not a first derivative. And actually, it doesn't matter in solving the equations. So if I turn this into a first derivative, the behavior is identical. You can show this numerically. It's physical, but I don't have time right now to explain it. If you want to ask during the coffee break why it doesn't matter whether I make this a second derivative or a first derivative, please ask. Okay, so what does the behavior of the model look like? If I calculate phi of t as a function of log t for, let's say, small lambda, it looks like this, and then it starts to look like this, then it starts to look like this. And then in the schematic model, this is about a half. You get a plateau, and you for above the critical lambda, and I don't know if it's 1 or 4 in the units I've used. Let's just say it's 4. Then you get a freezing of the dynamical correlations. And this was already known in 1984 in a paper by Leuthauser. They were already looking for a glass transition in the confines of this theory. And they argued it had to be a glass because S of Q is not the S of Q of the crystal. But as you plug in S of Q and the peak gets a little higher, this is happening more and more. And eventually the dynamical correlations arrest. But they arrested without any input that is related to periodic structure. So it has to be a glass. And then they made physical arguments that are related to the question that was just asked, that there should be this nonlinear feedback effect, that you get cages in the liquid, and the cages get a little tighter, and the first peak of S of Q goes up a little more, and that makes, through this feedback of the memory function, everything get much slower in a very nonlinear way. Okay, and eventually the system will just freeze. All of the properties here are exactly as I said. There's a power law decay into the plateau. There's a power law decay out of the plateau. In this simple model, the terminal relaxation is exponential in time. But if you solve the full wave vector dependent one, this is a stretched exponential. It comes from the coupling of the different k's. So you superpose pairs of different k's, and that gives rise to superpositions of exponentials that can be fitted as a stretched exponential. It has a time constant and a beta that are k dependent. The other thing that I didn't say is the relaxation time diverges in this, like lambda minus lambda critical to the minus gamma, and gamma is 1 over 2a plus 1 over 2b, where those are the exponents of the power law decay into the plateau and out of the plateau. Okay, so you get a power law divergence of the relaxation time. Mm-hmm.
If you send lambda to 0, don't you get like a 1 cos electron?
Yeah, that's why I think maybe we'll just, as I said, it actually doesn't matter for the critical properties whether this is a double dot or a dot. But if you like overdamped dynamics, let's say we think about a Brownian system, this actually would work out even in this theory to be a single derivative, and then everything's the same. Otherwise, it's true. And if you look at Leuthauser's paper, he has the double dot, so the small lambda behavior has oscillations in it. But then again, the dynamic structure factor at certain wave vectors, let's say low wave vector in a regular fluid, has oscillations too. These are just sound modes. So that's not unphysical. As lambda gets cranked up, even with the double dot, you lose all coherence, and you start to get this plateau, and then you get the decay from the plateau. Yes? Phi is basically, let's say, a proxy for f at the peak, the structure factor. Just the typical dynamic. So it's just the schematic version of fkt at the most prominent wave vector. Yeah, it's actually not totally trivial to do, but almost. That if you take a very simple approximation, I think maybe you add 1 to the structure factor, and just assume it's a delta function of structure, plug it into that equation, you can collect all constants, and you remove all the coupling between q minus k and k, and you just get a single equation for a single entity, which is a single dynamic structure factor at one wave vector, which we'll call phi. All right, so if you look at how well this works, it works really well in a certain sense. So obviously, it predicts a glass transition at temperatures that are way too high, well, which we'll talk about a lot. And maybe you should expect that from a mean field theory, right? If I do Curie-Weiss theory on the icing model, I get a critical temperature that's way too high. But actually, there's other ways to think about what that means. Maybe also what it means is just the dynamics as predicted by this kind of equation is right. And when it freezes, it tells you there's some other physics that should be going on. And that's what the p-spin model tells us. So we'll talk about that soon. Okay? But if you do a simulation and you fit the relaxation time in your true simulation to something like t minus tc to the gamma, minus gamma, you extract a fitted critical temperature, which is not a very high temperature. Okay? It is something like, it's something where the system is slowed down by about 4 decades of relaxation time. So it's very far from the glass transition. That's where that critical lambda would be. And in the real model, that's where the critical temperature would be. Okay? But what you can do then is say, well, if I use that as my critical temperature, and I scale everything by a distance from that critical temperature, and I calculate, for example, what the dynamic structure factor looks like, it actually fits very closely on top of the simulation until you get very close to the critical temperature. So over, let's say, 3 decades, you can quantitatively match Ludovic's simulation by doing the scaling. It's a little bit, it's ad hoc to do that, but that's sort of one way to see that you get some very reasonable properties from this. And in particular, also, near that critical temperature, you can fit the wave vector dependence of the peak, of the plateau. Okay, and the mode coupling solution for that at the transition really matches quantitatively the oscillations in k of the wave vector dependence of the plateau height. And one really remarkable aspect of that is that it was thought it didn't work well for more complicated systems like silica, okay, SiO2. And in SiO2, it turns out that you have, directional forces, directional interactions. And some of the approximations that are standardly used to reduce the vertex to this very simple form might not be applicable. So if you relax those approximations and don't make them, and then you plug that into the mode coupling equations, you actually get a beautiful matching of the plateau wave vector dependence, even in silica. And that was kind of interesting. So there's a lot of hints that this works very well in liquids over some very restricted range of temperatures. Okay? Yes?
So, I guess this is the theory developed for equilibrium liquids.
Yes? So from the way I've done this theory, it's not very good for doing that. And actually, that's one advantage of using field theoretic approaches, because there you separate, and sort of in the way that Leticia talked about the Martin-Sigier-Rose approach, there you separate out the response field and the correlation field separately, and you keep them separate, so you could generalize things. This equation has been derived very, very recently from a field theoretic approach, but it took about 8 years to do it, and I'm not 100% sure I believe the derivation isn't cheating. Well, no one has done that, as far as I know. Who has done that? No, what Latz did is he used liquid state theory, and he used the time-dependent projector to get the aging behavior. But that, to me, I have no idea whether his theory makes sense or not. But from the field theoretic approach, you can generalize things to an MSR-like way of doing it. And it took many, many people, including us, to fail, and Giulio to fail, and other people, to eventually actually rederive exactly this equation from field theory. And presumably, if that derivation is right, it's only like 2014, then one should be able to also generalize to out of equilibrium in that sense. But no one has done that. This is all equilibrium, right? This is all at the critical temperature or above it. There's no aging here. But you can solve the equations below the critical temperature, and what you do find is, the plateau just keeps going up. So you can go, if lambda equals 4 is the critical coupling in this model, I could simulate it at lambda equals 5, lambda equals 6, and it shows sort of the right behavior. But it doesn't say anything about two-time properties or fluctuation dissipation or anything like that. Yes?
Looking at the equation for phi, if I'm curious about dynamics,
Mm-hmm.
phi dot equals 0,
Mm-hmm.
that equation gives me phi equals 0.
Right, that's always one solution. So there's always one trivial solution, and there's always one non-trivial solution. And actually, it took a really interesting mathematical proof to prove that there's one unique non-trivial solution, which, if you're interested, I can send you the reference for.
Right, but I just want a quick answer for plateau. Plateau is really flat, right?
Yeah. Well, in the critical phase, the plateau is a infinitely long, slowly decaying thing that has a power law-like behavior. But yes, I mean, as I go up here, but remember, phi of tau had some dynamics also at earlier times, and this gets convoluted back through this term. So trust me, there is a solution always that is stable and non-trivial that has non-trivial behavior. But it is kind of interesting that, I think when this theory was written down, it wasn't clear at all that this was the case. And there is actually a real proof of this. Okay, so I have like 10, 15 minutes. So in the notes, I had worked out another example using memory functions and so on of showing the utility of the approach. I don't have time to do it. If you're interested in the notes, you can go through it. We've talked about some of the properties of the solutions here. And there's one other thing that I think is interesting about it that shows that it's not a completely, it's not a completely ridiculous theory. So if you look in the notes, you'll see that the comparison with computer simulation, if you make extrapolations the right way, are actually quite satisfying over a limited range of temperature. They're very, very satisfying for the behavior of the plateau. It really gets this very well. And it gets some of the fitting well, such that if you try to scale the behavior from the distance of the transition temperature compared to the simulation scaled from the distance of the fitted extrapolation of the power law behavior, in a real simulation, you could fit to T minus TC to minus gamma and try to get a TC. So if you do everything scaled to the distance of the transition, then you get quite a reasonable behavior for all wave vectors. That is semi-quantitative. It will look just like, and some of those graphs are shown in the notes that are posted. There's one other thing that I wanted to mention before we stop that's really interesting, which is, because this is a fully microscopic theory, it has full predictive power. So let me just give you an example that people don't so much care about, but about 15 years ago was something that people were very interested in. So you could take a system, let's say a colloidal system that is a proxy for hard spheres, right? And then the interaction potential is just a hard wall. And you can induce by depletion interactions, by adding some polymer depletant that has, let's say, a controllable radius of gyration. So this is the radius of gyration of the polymer. You could force by entropic interactions a short-range diffraction between these spheres. So basically what will happen is when the spheres get close enough, you'll get polymer everywhere, but there's the space between the colloids is too small to fit polymer, and there will then be an entropic force that pushes the colloids together. Okay? So what you can do is you can turn, a hard sphere potential into something that actually has a controllable well depth. The depth is controlled by the amount of polymer that you add, and the range of this is controlled by the radius of gyration of the polymer. So you can actually do really controlled experiments. Okay, and the reason why people got interested in this is that mode coupling theory made some interesting predictions about how dynamical patterns change when you when you turn on a very short range, let's say something like 1/10 of the particle diameter range, sharp attraction in the system. So basically, now you have a true U, and so if you plot, let's say, volume fraction on this axis, and let's say, I should do it like this, U over T on this axis, then when I turn off the depletion interaction along this line, I just have a hard sphere glass somewhere here. Let's say it's, 60% volume fraction or something like that. So what mode coupling theory predicted is if you turn on these attractions, okay, you would guess that you've already got a system that's vitrified, and now on top of it you add some glue, and so the system is just going to be a stronger glass. Right? You've taken a hard sphere glass and you've glued it together, but actually what happens is the glass transition line moves this way, meaning you melt the glass. So if I induce the short range interactions, actually dynamics speeds up. Okay. Now you can post facto, you can think about why that should make sense. In mode coupling theory, the reason why that happens is the peak of the structure factor actually goes down, and it moves a little bit to higher wave vector, and the other peaks start to go up. Okay, that's what happens in the structure, and that basically induces a melting of the glass. Okay, and then, however, if you add enough glue, this should turn around. So there's a reentrant behavior that's predicted. Okay, and it also, I don't have time to discuss it, but there are different kinds of mode coupling solutions that often exist when you have sort of the intersection of two different kinds of glass behaviors. You might call this the repulsive glass, and this the attractive glass. And then here's a different kind of mode coupling singularity that we're not going to talk about. But the bottom line is the prediction for FKT in the vicinity of this critical point is that it decays logarithmically in time. Okay, so mode coupling theory made some very specific predictions. They were all before the experiments. Basically, the predictions are that you have this reentrant behavior where you go from a glass to a liquid and back to a glass. Okay, that the introduction of attractive interactions actually speeds up relaxation, and that somewhere in here you get a new kind of relaxation that isn't, the plateau sort of goes away, and you get this power law, this logarithmic relaxation. And I would say this has actually been pretty satisfyingly verified experimentally. I mean, it's not, again, there's some degree, well, certainly this is true. You definitely will speed up relaxation by adding attractions. That's incontrovertible, and that is seen in computer simulation and experiment. The logarithmic behavior, it's certainly true that the relaxation patterns change as you sort of move through this cut. And so this is very interesting, right? That's something that's very hard to do in a theory that isn't fully microscopic, meaning that, it's not, here it's really just bulk thermodynamic behavior and structural information that you need to actually calculate what you get out. And you can just do it and see what you get. And so that's an example of that. So that's very nice. As I said, there are numerous failures. One of the biggest failures, as I mentioned before, has nothing to do necessarily with whether or not this is a useful theory. It depends on your interpretation, but it's that you get the feedback is so strong that you get a glass at very, very high temperatures or relatively low densities. So, you could even argue whether there is a true glass transition for hard spheres, but if there is, it certainly isn't where mode coupling theory predicts it to be. Mode coupling theory predicts it to be somewhere around 50% volume fraction. That's like the crystallization temperature of the, or density of the hard sphere suspension. So that's really not, where all the action is happening. So the question moving forward for the last lecture is, what does this mean? And what we're going to talk about is the perspective of this kind of equation from the standpoint of mean field spin glasses. And I will, at the very beginning of the lecture, show you that in the p equals 3 p-spin model, this equation is exact. That is the exact equation of the dynamics. So therefore, the behavior is like this. And Leticia drew this on the board yesterday. Okay. What actually, we'll talk about what this means. I mean, in the standpoint of that theory, you can think about an energy landscape. In the phase where you're coming from the weak coupling side, what it means is that the system just has one trivial free energy basin. But as you start to approach the critical temperature in the P equals 3 P-spin model, you will start to see this plateau appear. As Leticia mentioned, this is the hallmark of something I think Ludovic talked about, which is the Franz-Parisi potential starts to look like it wants to form a second minimum. Not yet, but it's starting to look like you need a Gibbs construction. Or what Leticia mentioned, that there's a threshold on the landscape. And then the system will freeze at the critical temperature. And in the confines of that model, what happens is the configurational entropy will jump non-trivially. Okay, the mode coupling theory in that sense is no longer valid. You can ask within the confines of the exact model what happens below the temperature, transition temperature, and of course then you get all this interesting aging behavior that Leticia worked out analytically exactly 23 years ago. 23 years ago. in a very highly cited, very important paper. But you could also ask what it means from the standpoint of going beyond mean field theory. So now you have a non-trivial free energy landscape, and as Leticia mentioned, you have activation. And basically, mode coupling theory might just be a part of a more global perspective on glass theory, where the high temperature behavior in the liquid phase is described by this theory. But when mode coupling theory freezes, then more interesting things happen, which are related to activated local processes. One other thing that I want to mention is that in the P-spin model, and as maybe I'll get to tomorrow, even in liquid state mode coupling theory, there is a diverging dynamical correlation length as you get to this transition. So chi4 actually diverges, which is interesting. And it sounds weird that, in some sense, a mean field theory has something to say about growing length scales, but of course that's not so weird. I mean, as I mentioned at the beginning of class yesterday, in the icing model, mean field theory also tells you you have a growing length scale. It's the growing length scale of the domains, right? It's not described properly. You get t minus tc to the 1/2 or minus 1/2 instead of 1/3 in 3 dimensions, but it's qualitatively right. And this will happen here too. You'll get a chi4 with a peak that diverges. That can also come out of a theory sort of like this, but a lot of work has to be done to show that. So that's what we're going to finish on. We're going to talk about what the meaning of the theory is from the standpoint of whether it's really a good mean field theory or not, what the solutions of this equation look like in higher dimensions, and basically what the correct mean field theory of the liquid state is in high dimensions and how that connects to spin glasses and so on. So thanks.